Who wants to learn about physics movement? And making it fun, subjectively, because fun is entirely subjective. This will be the only mention of free body diagram, so I guess that's a content warning for some people. I'm not going to be mentioning that ever again, sorry. All right, physics movement. So about me, about Beto, or you may know me as Alberto. I'm an indie dev generalist. Done a bunch of things. Done some things for Team Fortress 2. Done some things in VR. Done some things in a 2D platformer, multiplayer, single player thing, first person shooter type thing. Yeah, I've done a bunch of things, but mainly I've done Hover Drive, the vehicle platformer that everyone likes. Hopefully, maybe it's not for sale yet. We'll find out eventually how that goes. So physics movement agenda. We're going to talk about my opinions on movement in games because that's what a lot of this is. There's some things that may not be objective, but most of it is subjective at the end of the day. And then also an approach to movement design, which making this presentation really made me think about how someone might approach designing movement in games. I was like, how do I do this, right? And then the last part will be a breakdown of a part of hover drive physics, but I'm trying to keep it relatively straightforward and as non-confusing as possible. So I'm gonna keep an eye on chat to see if anybody has questions, but feel free to stop me if you would like me to explain something further at any point. So without further ado, I'm gonna start with a disclaimer. My word is not the end-all be-all. You can do things however you want at the end of the day. And I'm not a classically trained software engineer, so I think a lot of my approaches come from just a design part and not really like, this is the best way to engineer this solution. And it makes more sense to me that way because I didn't really study software engineering professionally. And I don't play games. I think my top 2 most played games on Steam are TF2 and Deep Rock Galactic, but TF2 has like 3,000 hours and Deep Rock Galactic has like almost 300. But like the next couple things in the list, I like, let's see, Gary's Mod, I last played that 6 years ago. Sea of Thieves, I last played that over a year ago. And then 50 hours in Tabletop Sim and Ultimate Chicken Horse has like 40 hours. So yeah, that's my other disclaimer. I've tried a bunch of other games, but I don't really like play them that regularly. So now with that out of the way, I'm going to give the number 1 rule for fun movement in games. Yeah. Momentum. That's my number 1 rule. I think I'll get into it later, but I've got other things. I lied. There's number 2 rule. It has to be predictable. And then the number 3 rule, I also lied again. Nuance. So the 3 biggest things for movement in games to make them fun are these 3 things. Momentum, that's predictable, but with nuance. Now I must talk about those. So what better way to show that than with examples of what I mean? All right, here's the first video, Mario Maker. I played a lot of Mario Maker, and I really like their... I got to try the different forms of Mario movement throughout the generations, because Mario Maker has a bunch of different ones. But one thing that I liked about it is the momentum you can pick up as Mario. And one of the best ways to show that is with the Kaizo levels, which are the super difficult movement levels where you got to really put your movement skills to the test. But for instance, here I can just mention this like jump right here. You're moving to the right off of the shell, and you have to keep your momentum to catch the Yoshi that's falling in the air. And then you're jumping off this boo to jump over this thing. And a lot of these things rely on keeping your momentum throughout the movement. And then one thing that's subtle about Mario movement that I don't know if a lot of platforming games pick up on is Mario movement isn't strictly, it's not instantaneous. So when you push the right button or the left button, Mario doesn't instantaneously move at that full speed right or left. There is some acceleration that happening over time. What that also means is when you're in the air, you can adjust how fast you're going left or right by ever so slightly letting go of the right stick or ever so slightly tapping left on the left stick. And that will adjust your velocity in the air for landing a particular jump. And then the second example is Celeste. Celeste actually has more or has less of an acceleration. So when you tap left or right, you actually do reach your top speed very fast. But there is still a little bit of acceleration. But the momentum comes from the dashes that you get. So, I mean, even immediately here, you're going to land on this platform here and then dash to the right. And then you get to dash immediately after touching a single piece of the ground. It's like the frame that you hit the ground, you can dash again. So you can really keep your momentum that way. And you can also dash again in the air to get this up here. So you get a lot of opportunity to keep your momentum going. I mean, here you land on this thing and then just immediately you dash and then jump again. And that was the point I was making there, is momentum. And then some examples of lack of momentum. These are two games with platforming in them, but I wouldn't necessarily say that you play them for the platforming. And one of the reasons I think that is because of the lack of momentum. So I very distinctly remember watching this trailer 9 years ago, and I'm thinking to myself, wow, this looks not fun to platform in. And then I think one of the reasons why I made that thought was because the Cuphead guy, Mr. Cuphead here, he moves instantaneously. When you hit right or left, his speed is perfectly exactly at the maximum speed that he moves. Which, it can be fine, because Cuphead is not strictly a platformer. It's a bullet hell game where you have to avoid the bullets mostly. So in that regard, like, that sort of movement is perfectly fine. But when it comes to platforming, it doesn't necessarily lend itself to fluid movement. And the other thing is there's a dash in here. I don't know if they're going to show it in this video, but the dash is faster than your regular walk speed. But as soon as your dash is over, you immediately get shoved back into your regular walk speed. So every time you dash, you just get reality checked about, oh no, here's actually your real speed, here you're supposed to go. I don't think they're going to dash in this, but... Oh yeah, there's the dash, but he stopped immediately. So not the greatest example of what I mean there, but... In Cuphead, there's that, and then the other one, Little Kitty Big City. This is a 3D platforming game where you're a cat, but the jumps here are very methodical. You gotta hold down the spacebar and then charge up the jump distance, and then you just jump where the feet are gonna land. It's like, yeah, there's 3D platforming, but not exactly the most riveting platforming experience. And like, it's not trying to be. You play this game for the cute cat, you don't play the game for the excellent platforming, right? So it's okay to have different types of movement, but this is not what I'm gonna be talking about. All right, so momentum. How do you get momentum in games? Or what's a good example? Another good example. Since I played 3,000 hours of TF2, that's a great example to talk about momentum. And these jump demonstration maps are some of the best examples of showing like how much momentum you can get in this game just from rocket jumping here, right? So at no point did he ever stop moving. He's just keeping all his speed throughout all these jumps. And then this is also a good example of nuance in physics movement, because in this game, how would you think the rocket jump works? You think, okay, you just shoot down at your feet and like the rocket comes out from your screen and then it just hits your feet in the middle. But that's actually not what happens. In this game, the rocket actually spawns from the right side of your character because you're right-handed. So if you're pointing straight down and you're like trying to see where the actual rocket goes, it's going to go slightly to the right and slightly in front. So like the top right corner of your character. And that becomes important because if you're rocket jumping along a wall, you're going to be rocket jumping with the right side of the you're going to be rocket jumping with the gun model facing the wall. So jumping to your left will be slightly less effective than jumping to your right because the rocket's going to be closer or further from your body. And you can see in all these clips, they're always on the right side of the wall. And that's just one of the nuances. But what that lets you do is that means that the consequence of that is depending on where your gun is or your rocket is aiming, it will change how much force you get from the rocket jump. So you can very carefully tune exactly how much force you want based on how you're aiming, because the rocket jump doesn't come from exactly in the center. If the rocket jump was coming from exactly in the center, you get no way to tune how much force you get, because you're always going to get exactly the center, and that's exactly the same amount of force every time. But because it's not exactly coming out of the center, you can tune it to the situation. So that's some nuance and momentum. And then consequently, there's this mod coming out called Momentum Mod that has all the Source Engine movement tech as a game, and it's called Momentum Mod. I feel like that's pretty fitting. So this is all great and all, but how would you even like make a movement design doc? Because you can make design docs for a game in general, but how would you like design doc a movement? Like my video game. The movement should feel good to get play. Like, yeah, obviously, but like, what would you even put here? And this is the part where I don't really have a great solution for not programming, because I think programming movement is sort of integral to how you implement it and how the end result turns out. Because some of the quirks of how it's implemented result in the end result. Like, I'm sure the game designer for TF2 said, let's add rocket jumping, and that was the game design. But it was up to the programmer to decide where to actually like spawn the rocket from. And maybe a different design element was, oh, the player's right-handed, so everything should come slightly from the right of the character, right? So that when you peek around walls, you can shoot like the right side of your screen first instead of coming out the left side of the screen. Like maybe those two were the design elements that were in the design doc, but then the side effect was that rocket jumping now has all this extra nuance from that. So some tips that I have thought of for making a design doc about movement is just describe the goal that you want in excruciating detail. And we can try it with some of our favorite games. Then Minecraft is a good place to start. So I actually have it right here. You should be able to see that, right? Do you see that? Minecraft now. And I literally built this like wall section here with some stripes. And something you can do is, let's analyze Minecraft's physics. So how fast is the character accelerating? What's your top speed? Like, how are you jumping? I'm actually just gonna be ignoring jumping. But let's just like, if we walk to the left and right, like there's a speed associated with that. But what is that speed? So you could take a video of this and then count the frames and see how many frames it takes to cross each block. You'd be like, okay, I'm moving like 4 blocks a second or something like that. And then how does that change when you're jumping? Or how does that change when you're sprinting? And how does that change when you're crouching, right? So you have all these layers that affect your base movement speed. And then you can start to build that description of what you actually want. So, I mean, one of the quirks of Minecraft movement is when you're sprint jumping, you're actually moving slightly faster than if you're just sprinting normally. And I don't know exactly why that happens, but one of the quirks is that you get just a tiny little bit of a speed boost upon a jump. So like when you first jump, that's slightly faster than if you were just like holding W. So you might want to describe that in your design doc. You say, okay, when the player jumps, just get a tiny little boost, right? And then you can see some parkour gameplay for the extra nuance that comes about just from the slight quirks in how it's programmed. So you get slight air movement, and because you get the different speed based on your sprint jumping, you can see this person's jumping during the whole time. Is on the flat section, it's easier to tell. We have the time, because jump sprinting is faster than just sprinting by itself. Suddenly this platform that's flat becomes more of a challenge, because if you just had a hold W, okay, well, you just hold W in like the shortest line possible. But now that you have to hold W and jump, well, now you have to time your landings so that you aren't missing a gap. So if he jumps now, he's going to want to land in this block. He wants to land on this corner, but he could land on the edge to get like a shorter line, but then you might hit the wall here. And then this gap here has to be calibrated to this jump, because if not, if it was a bigger gap, then he would have fallen down, so he'd actually have to take a wider turn around it. Or then even there too, like he landed on, or they landed on the lower block here, right next to the waterfall. So they landed on this dirt block here because they're jumping, right? And then they have to land on this one, and that lined them up for the rest of the jumps. So just because of that one change where you get a tiny boost from jumping, you've introduced a whole lot of extra nuance to how you approach movement in Minecraft. And we don't have to do all those calculations because the Minecraft parkour wiki already did all the math for us. There's all the movement equations for Minecraft. Great. That saves us a lot of time. So one thing that I also want to talk about is macro versus micro movement, where the gameplay is sort of defined by the macro movement, and that's sort of holistically what you want like movement in the game to be, just generally. But player expression and the fun sort of lies in the micro movement, wherein provided by the general movement rules, how can you ever so slightly adjust your movement in the millisecond to millisecond, frame by frame aspect to get more unique gameplay out of that. I've got two examples for that here. In this game called Ram War, it's also based in Minecraft. There exist jump pads. And so jump pads are defined as an overarching movement rule. Like there are jump pads in the game. And maybe the level design of the map will dictate where the jump pads go. But just because now that there's jump pads in the game at all, now all of a sudden you get opportunities to do some neat things. So like right here, the brown, where'd it go? Right here, this brown spot on the right, that's the jump pad. And then these the red and purple here are the regular ground. And what's going to happen here is there's going to be an explosive arrow. So this arrow that just landed on the ground, that's an explosive arrow. There's going to be a radius that explodes around it. There's a couple options here. You can either run away, back up, keep pushing forward, or you can choose to take the jump pad, and now you've jumped up and you've dodged the explosive arrow. I mean, that was pretty cool. But the level design dictated that jump pad because the jump pad goes into that opening that's in the upper left there. But you didn't have to do that. It's just by nature of there being a jump pad there, you've introduced more options for the player to express what they want to do. And then they do take the window here. And then the second example of micro versus macro. So in this example, the macro was the fact that there's jump boosts, but the micro was in the combat situation using the jump boost to avoid an attack, even though you aren't taking the prescribed route for that jump boost. And then for Marble Blast, the marble game, very macro is you're a marble with physics. It can roll around. But maybe deliberately, the level designer put these lips all around the edge of the course here. And not all the levels actually have these lips, so it seems pretty deliberate. But because of the physics, you can hit the lip of the edge there and it bounces the marble up and you can just skip that whole gap. And that's just a quirk of this physics engine, is when you hit that corner, you just get bounced up. Yeah, so he just bounced off 2 corners. Like, that was pretty cool. But like the macro movement here is just your marble rolling around. And then the micro movement is adding these features in the levels that let you get some more skill jumps out of it. I mean, you can't get any more simple than that, just a marble rolling around, right? Anyways. So the other thing you can do for designing movement is using graphs. So this will be great. I like using Desmos a lot because you can just plug in the equation and multiple versions of the same equation and just see how it affects the trajectory of something. So in this case, you can say, let's say you're programming, you're trying to implement the acceleration curve for your character. You don't want instantaneous movement. That would be like the blue line, where as soon as you hold the right button, you get maximum acceleration. It's perfectly linear based on how you're pushing it. 1-to-1. Maybe you want some acceleration. So over time, you hold right, and then it slowly ramps up to the maximum speed. You could try quadratic, but that might feel a little bit sluggish. It'll take over a quarter of a second, if we're looking at this as the x-axis as time. Like it's already half a second, and like you're still barely moving. So maybe you want something faster. Well, now you can start stacking equations to get a more interesting or more desirable curve. So let's just stack x, which is linear, and add in cubed, which will ramp up even faster than squared. So now we do x plus 2x cubed, and now we get this red line where you start immediately moving forward when you press right, because at the 0 you're already moving linearly. But you're going to ramp up a lot faster than if you were just moving perfectly linearly. And you can start doing crazy stuff and adding a bunch of extra exponents and stuff. I mean, the computer will just do it instantaneously, so it doesn't, and you'll never really see it. So feel free to just make a crazy graph. And then finally, use parameters. So if you're working with a programmer who's implementing all this, they should be giving you as many parameters as possible. Actually, so many parameters. Here's just some of the parameters for hover car. You got forward acceleration, backward acceleration, turn strength, turning friction, power slide friction, power slide turn multiplier. The list goes on and on. Some of these you don't modify, and they're just there to see at runtime, just to see what the number is under the hood. But this lets you fine tune. You've got the general, right? Like you have a generally like you want to accelerate and some amount. But this lets you won't know exactly what number that is until you actually play test it and try it out. So this lets you try it out without having to bug the programmer for making every single tiny change. So wherever possible, use parameters for everything. And then finally is actually play your game. I want to insert some clip. I forgot to actually get a clip, so I have the game open right here. Actually play your game and get good at the movement. Because how can you possibly try to implement movement physics in game that is fun if you don't even play it yourself? You're like, oh, I think this is fun, but I don't even know. So I mean, and one of the things you can start exploring is how do you even break your own movement? Try to break your own movement and discover some of the tech. I can't do it because I'm in edit mode. This is awkward. Switch the controller. You can start discovering some tech in your own game. So I discovered that my game has drift smuggling because you get a boost from drifting, but you can smuggle that in the air if you jump and then let go drift. So all of a sudden that opens up a lot of possibilities for skipping whole levels. And I can just fly across the whole level. Stuff like that. So yeah, actually just play your game and get good at it, discover how the movement breaks, fix any bugs that you might deem as undesirable, etc., etc. Anyway, but now let's talk about hover drive, the vehicle platformer. How would I approach designing a movement like this, right? Like, given what I've said before. So, I mean, one of the main criteria I want is that any surface is drivable. So that immediately kind of changes how you want to approach implementing these physics. And then something else is you want to jump and boost with air control. Because it's a car game, and most car games you kind of just go off a ramp and you're at the whim of the physics engine to like tell you where to land. Maybe sometimes you can like adjust your total distance, but in this game I want you to have pretty good control over where you're going in the air by allowing you to jump and also boost in the air. So now let's look at some inspirations for where I got these ideas. There's some videos here. Hopefully, let's see. Let's start with the Hot Wheels one. This is Hot Wheels World Race. It's a racing game where you play as Hot Wheels, and there's lots of twisties and curvies. And it's not explicitly anti-gravity, but I mean, you're a Hot Wheels car, so like, I mean, that's pretty cool right there. Like, oh wow, you're twisting and turning. It's like, oh, now there's like a track above you. That's pretty neat. And then I don't know if this video has it, but you can also do tricks in the air. I was like, oh, this is just hover drive. Actually, this is the game. Yeah, this is actually the game, right? Are there any ramps in here? I did not check that. There's wall riding. Oh yeah, here's a jump coming up. Take the ramp. Wow, look, tricks. Nice. Wow, look, more tricks. Nice. Okay, there's some inspiration. I got this other inspiration, the Lego racing game. It's very bouncy suspension, right? Like, oh, that's like a hover car, kind of. It's very bouncy. But something that I don't like, this is very unpredictable, right? So it's got physics, great, but it's not predictable. So it kind of sucks to play if you're like trying to use the physics in like a way that you want them to. So we don't want this. We want the bounciness, but we don't want the unpredictability about it. All right. And then we also got Cluster Truck. Cluster Truck has great momentum. You can jump and you can wall ride on the trucks themselves, but wall riding kind of like catches you and then like pulls you back up. It's not instantaneous, so you have to grab like the top of the truck and not necessarily like you can miss a truck is what I'm saying, is if you don't hit the top of it first. And this guy is gonna keep failing. That's okay. All right. And then some other inspirations. Mario Kart 8. You got the anti-gravity tracks, classic. Tron Legacy, great reference for visuals, aesthetic. F-Zero. F-Zero's got a lot of speed and very fast and interesting track design, but I don't really want to do that. I want to lean more into like a Mario 64 type platforming experience where, yes, you can go fast, but it's not just a straight line. Like there's actually more intricacies involved with the level design. So those are the inspirations. So how did it start? Like, how do you even like start making a hover car? This was way back in 2019. I didn't know how to program. I just followed an Unreal Engine blueprint tutorial. I found the original one that I looked at. This is probably the one that I don't know if it's exactly the one, but it's pretty close. You know, just pause the video every 10 minutes and screenshot it and then like try to copy it as best I can. And then we get this, right? I was like, ooh, I'm hovering. Wow, look at that. Wow, there's a little bit jank there. Oh. But you know, I was like, let's try wall riding up here. Like, ooh, oh yeah, I'm on the wall now. Wow, like that's crazy. Whoa, I'm kind of stuck. Whoa, do a flip. Nice. Kind of cool, but kind of unwieldy. Well, it works on stairs. It's pretty smooth over stairs. Okay, here's the actual wall ride attempt. And oh wow. Oh, I'm on the wall. Nice. But I'm kind of slipping. I have to like, oh, and then I fell off. Yeah. So like the basic ideas there, execution, not so much. Fast forward to the next semester, fall 2020. I get let's actually try programming for once. Let's try learning C#. This is the exact tutorial that I followed all that time ago. And I was like, well, look, it's the hover car. That's the game. You can hover, and it's like it's moving around. And it's like, ooh, wow, floaty, nice. I was like, all right, let's see my attempt. There's the hover car. Yep. And you see that's the same car. I still have the same exact car model from way back then. Has not changed since then. You know, you can drive around. It's like, ooh, you're hovering, nice. And then the last part has the interesting parts of it. Oh, let's go up the ramp, nice. And then can you go around the cylinder? You can go around the cylinder. Look at that, cylinders, crazy. Crazy stuff. That's the hover car. That's the whole game. We're done. Game's done. We can publish this to Steam. We're gonna get $1 million. It's gonna be great. Actually, just kidding. How it's going? Oh, yeah. I don't know, guys. I don't know if we can do this anymore. See, this is like biblically accurate. It's raycast, I think. I'm not entirely sure what's going on there. Yeah, games are hard, guys. Who didn't tell me that before this? Great. So what even is a hover car? How would you even how do you define that? It's great we want to hover, but what does that even mean? Well, obviously the vehicle has to float above the surface. Okay. Good place to start. And the second thing that's important is we don't want the hover to interfere with jumping. We don't want to be that Lego car where you just discombobulate whenever you land on a surface. So it's important to mention as one of our design requirements. All right, floating above the surface, simple enough. You just have a target height over a surface. That's your hovering. Great. All right, some other criteria that we need to define. Any surface is hoverable. What does that actually mean? Well, it would mean that transitions between the surfaces have to be smooth. So if we're approaching a wall, that's going to be a concave surface. We want to be able to go around that pretty smoothly. But that also means that the opposite has to be true. If we go around a convex surface, that has to be smooth. So that's part of our design requirements is we need smooth transitions between concave and convex surfaces. All right. What else do we need? We need grip. We need grip. Grip to be maintained at speed. So the car has to stick to a surface at speed. So if we're going fast, like you can imagine a cylinder or a circle, you should be able to stick to that circle no matter your speed. Great. You shouldn't fly off. And then the other thing is you should have rotational freedom in the air. This will give you control over where you're going. So we got pitch, yaw, and roll. Yes, that's what we want for air control. Also, this is got to be the only applicable time of using a 3D model in PowerPoint. It's pretty neat, if I do say so myself. And then we got boost to any time. So you can boost on the ground, you can boost in the air. That's going to be very important for feeling snappy. And the air boost must be an additive force. You don't want to ever lose your momentum because you decided to boost. You don't want to be like Cuphead. So your boost must add on to whatever speed you already have. So you can be going, you can be boosting, and then you can be boosting in the air. That's nice. You could be jumping and then boost to keep your forward momentum in the air. Very important. All right, we gotta get some more specific. Let's get more specific now. That's the general things, right? We got floating, we got smooth transitions, surface grip, air rotation, and boosting and air boosting. So how do we start actually implementing this? What do we go from there? Let's start thinking about what floating means. And then all the 10 million edge cases, of course. We're going to find so many edge cases. But that's where the nuance lives. That's where the fun lives. So hovering, right? How do we want to actually define that? With raycasts, of course. 1 million raycasts. We can start with the basic 4 corners raycast. This is what the original tutorial that we saw earlier was. You do a raycast in each corner of the car, and that's going to be your hovering. This works great on a flat ground because your target height will be just the raycast distance minus the car distance, and you got to get to the target height. All right. Wait, who's Ray? I don't know. Anyway, smooth transitions. How do we define that? Well, in a concave surface, that's not a problem because our ray casts are pointing down and away, so they're going to be hitting the ground. But on a convex problem, we've already run into a problem because our ray casts are no longer, they're angling out, so they can't hit the ground anymore if the ground is like a square like that. So now we've already introduced an edge case where we got to have an additional ray cast to see the convex side. And then what is my target height here? Because if the target height is based on the raycast, well, that's going to be different on the concave surface versus the convex surface. Because on the convex surface, you're going to be a lot closer to the point of the shape there. But that's not where the raycast is. The raycast is at the corners of the car. And then in the concave scenario, like it's a huge space you got there. Like, do you need to define these distances separately, or what are you supposed to do there? I don't know. We'll think about that later. Getting a grip. All right. So how do we get grip? How do we stick to the surface? Well, the forces can depend on the surface radius. So you can imagine a centripetal force, right? Or like a ballerina spinning faster when they get smaller. The smaller the radius, the greater the force you're going to need to stick to the surface. If you've got a very wide radius, that's very close to a flat surface, so you don't really need a lot of extra force to stick to it. But then this also has to work when you're on the inside of the wall, right? So when you're on the outside of the circle, you want to make sure you don't fly away. But when you're on the inside of the circle, you want to make sure you don't crash into the surface, into the ground. Okay, so that's an edge case right there. And then, well, it also depends on your speed. Because what do you want to happen when you reach the edge of a curved surface? Do you want to, like, if you're going 50 million miles per hour here, do you want to like quickly shift around to the underside? Like that's going to seem pretty disorienting. Or do you want to like fly off the edge? Like if you're going at an edge really fast, do you want to fly off the edge or do you want to like wrap around the edge? But then like if you're going really slowly, you don't really want to fly off the edge there. So there's going to be some threshold that determines whether you stick or you don't stick based on your speed. But then also that depends on the angle. Because if you're going straight off the edge, well, I think you want to fly off the edge. But if you're going at an angle on the edge, well, maybe you don't want to fly off. Maybe you want to actually wrap around the edge. So there's a lot of nuance in this already. You got the radius, the vehicle speed, and the approach angle in just how do you stick to a surface consistently. Okay, well, that's pretty confusing, right? How do you get this far and do stuff? Well, let's break it down into two parts. So the first part is getting the hover plane. Okay. The hover plane will let us do a couple things. It'll let us smooth out any inconsistencies in the geometry and just get us a simple flat surface to work with. And then the second part is applying the forces on that plane that we've calculated before. So those are the two main parts. So how do we get the hover plane? What do you do there? Well, there's a couple, like you can do complex math and like geometry math. Well, I just took the brute force attempt. Just do a million raycasts. It works fine. Computers are fast enough nowadays. You do a million raycasts to get your plane, and then you just apply your hover forces to the corners of the plane. And this now lets us take care of the convex versus concave problem, because now the plane will be consistent, and the hover force doesn't have to worry about hitting the actual geometry now. But we still have a problem. What's our target height? So if the smoothed out hover plane is this green line here, where do we want the hover target height to be? Well, we want to be, if we just say it's x distance away from the surface plane, that works for the convex or concave situation on the left, but on the right, that means we're going to be crashing into the geometry, which is not what we want. So now we have to think about, okay, if we have the hover plane, then we actually want to push it out of the geometry. So for the left case, it's already pushed out of the geometry, so we don't really do anything. But on the right case, it's pushed out of the geometry, and now we're floating on the edge of the square. Great. So that's just for the hover plane. But now we can actually talk about the hover force itself. So we've got the green lines are the raycast. That's what's going to be checking how far away from the ground we are. And then the target height can be some distance, but the distance we actually care about is how far away we are from the target height. So if we're too far from the surface, our target height is measured from the ground to the target height. But if we're too close to the surface, then it's going to be the opposite. But what does that actually mean? It means that we can implement Hooke's law, spring force, which is linear, and that's what gives us the bounciness. Wow, like car suspension, there's springs. But that doesn't quite get us what we want, because remember we have to be gripped to the surface. So this is great for a flat surface, but it's not so great when you want to adjust the force based on you going around a circle. So this is where I implemented a hover force curve. And this was accomplished by stacking multiple equations in Desmos until I got a shape I liked, where the middle region is linear, and that gives you a nice bounciness. But the outside of this region is very exponential. So you very quickly ramp up the force a whole lot, a heck of a lot. Like you get, like your force in the middle might be like, I don't know, 50, 100 units of force. But then on the edges of the boundaries here, you're going to reach hundreds of thousands of units of force just to maintain the stickiness. So now we can visualize it with the car. So when you're close to the target height, your distance is going to be very close to zero. So a zero distance will give you zero force. Great. So if you're at the target height, don't do anything. You're great. Just stay there. But if we move away from the target height, all of a sudden our distance is really big. So our force gets exponentially bigger, right? And so you can imagine how going between these two cases, your force will change depending on how far away you are from the target height. And this is the basic simplification of how the force dynamically changes based on your distance to the surface. And this lets us take care of gripping around a circle. And it also works when you're going on the inside of a circle. And you can see here how if we just were using a linear, regular Hooke's law, then for this distance, we would be having way less force. That's like almost half as much force as we would otherwise have. So that's the hover. That's it. That's how the hover car works, right? Actually, just kidding. But what about gravity? I didn't even mention that. Did not even mention gravity. That's the whole point of the thing, right? You want to be anti-gravity. Well, the secret is that there actually is no gravity. There's none. The only gravity happens when you're in the air, surprisingly. So the hover force only has to worry about keeping its distance from the target height. And then as soon as you jump into the air, that's when true gravity kicks in and like starts adding to your car. But wait, what even counts as the ground? Because if you're a hover car, then what even is that? Because you don't have wheels to like touch the ground. It's all done by raycast. So there's more edge cases now. Oh no, not more edge cases. All right. So how do we do this? Well, we add an auxiliary force to the raycast. So the green line here represents a grounded, successful raycast. And then what you would expect is the car to pull itself to the ground. So if we have a valid ground surface, well then just literally do that. You just pull yourself to the ground on all the raycasts that don't have a valid force yet. So the red arrows represent raycasts that aren't on the ground. And so because they're not on the ground, but there are raycasts that are on the ground, we're going to add an auxiliary force to help us pull to the surface. And this helps us around corners where you might be going slightly too fast. Um, so it'll pull you down to stick to the ground and pull you around the corner. Does that make sense? I feel like this is like a pretty vague, arbitrary rule here, but hopefully that makes a little bit of sense. Anyway, that's actually how the hover car works. I do have some suggested literature here. I wish I'd found this left video when I started, but this video actually didn't exist until like a year ago, maybe. Um, it does a pretty good job of like visually explaining car physics in games. They put like little arrows everywhere. But the basic premise of the hover car is exactly this, minus the wheels. You just subtract the wheels, and like there's your hover car. They have it here at the beginning, actually. Here you show the forces there, right? Like, oh wow. Like this video does a great job of explaining the spring forces. Um, and then the other video here is the Mario Galaxy physics. Mario Galaxy takes a different approach, right? So my approach was to do all the physics on the car itself, whereas the Mario Galaxy has predefined bound like volumes that determine the gravity force. So you've got circles, you've got cubes, you've got discs, and you've got, I think, donuts as well. So they have all these predefined shapes. I mean, credit to Nintendo, their level designers knew exactly how to implement all these shapes really well. But that's all the shapes you get. So all the level design had to be limited to those shapes. But something like this kind of broke one of my design requirements where you want every surface to be drivable. So how do you how do you do that without, like, you don't want to put that on the level designer's shoulders to do that. You want the car to be consistent for any surface. And yeah, that's actually how the hover works. That's the end of the presentation. That is how the cookie crumbles.
Awesome. Thank you, Alberta. This was a really insightful presentation. I know I'm doing some physics-based movement in my game as well, so there's definitely a lot of interesting things to think about in here. Um, so for those in the audience, we can open up to Q&A. If you have any questions, feel free to start putting them in the chat. To give a little bit of time, I have some questions of my own, if you don't mind me asking.
Oh yeah, go ahead.
But with your implementation, how much of this like are you using Unity's actual physics system versus like just kind of doing the calculations and applying the updates yourself?
Well, there's not the actual forces. Oops, let me go to a different slide here. Let's go to this slide. So I'm just at the end of the day, I'm just applying forces to a rigid body in Unity. So the force calculations happen here. Oh, no, oh my gosh, here. So this distance gets multiplied by the hover force formula, and that is the force that gets applied at the raycast. So the Unity physics that are being used are like the rigid body is just the rigid body, and then I'm applying forces to that rigid body. Um, I did have to do extra checks for collisions because the Unity collisions by itself wasn't enough, and I kept falling through the ground. So I did have to add extra checks on top of that. But I mean, the regular collision is still there as like a failsafe.
Awesome. And then you talked about stuff like implementing a variant of Hooke's law to kind of create the spring forces. how often do you find um, trying to use kind of like existing formulas or things like that useful for things like programming physics in your game versus just kind of having to make up something yourself or kind of reinvent the wheel almost?
Well, real life is not game designed, so you can start with the kinematic equations that you learn in physics class as a starting point, but you very quickly realize that it's not very fun to move around with real life physics. In this example here, in this tutorial, they're using Hooke's law, and it's just a regular gravity force. And you can see how it's very floaty, and it's very slow to react. So almost as a requirement, you have to crank the numbers way up to get something that feels more gamey, more snappy. I think my gravity force is like 30 units. I think the default might be like 10, but I think my gravity force is like 30 or 40 units. Don't remember exactly. Oh wait, I have a screenshot. We go to the screenshot. What's my gravity force? Gravity. 85. My gravity is 85.
That is
So
very high.
yeah, that is I don't know what Jupiter's gravity is, but that's a lot. And the default is what, 10? So yeah, like I don't real life physics and the kinematic equations are a great starting point, but you want to apply some game design to it after the fact.
Awesome. Well, I think that covers my questions. You already kind of like Nick said in the chat, like there's so much to think about here. We'll take rewatching to get to fully parse it all. But yeah, thank you so much.